concept learning, and we say that we have a whole sequence of, we have a whole space of concepts, and what I want to do is, I want to learn the concept or hypothesis that best fits my data. Okay? That's what I want to do. And in our case, what it was is we had only 973 hypotheses to search for, so maybe efficiency was not a big deal. But in real life cases, you may have a large number of hypotheses, and in that case, you have to search very efficiently. So you have to wonder if there is an efficient way of searching and so on, right? And especially when the hypothesis space is very large or even infinite in some cases, then what's the best way to figure it out? And there are many algorithms for doing this, for searching through the hypothesis. We'll look at some basic ones. And what we will do is, we will use a particular structure of hypothesis. We have the whole space of hypothesis. But usually we can find some relationship between hypotheses, right? And what that specific relationship is, general to specific ordering. Right? And I'll talk about general to specific ordering, and I'll show that how that helps us to make the search process more efficient. Right? So what is this general to, what is a general hypothesis and what's a specific hypothesis? Right? So consider these two, H1 and H2. These are my two hypotheses. The first one says, if the sky is sunny, and I don't know what this was wind probably. If the wind is strong, then go swimming. And the second hypothesis says, as long as the sky is sunny, just go swimming. Don't have to worry about anything else. These are my two hypotheses. And if you look at these two, one says sunny and strong, go swimming. Other says just sunny, go swimming. And if I go back to my training data here, these two and the last one, well, these are all my training data. Let's see if my hypothesis works or not. First one said sunny and strong. Sunny, strong, go. Works. Sunny, strong, go. Sunny, no, not satisfied. So I'll put in no, so that's okay. Sunny, strong, yes, that works. And you can imagine sunny and strong work. So if I just look at sunny, that also works. Right? So both of these hypotheses will satisfy my training data. Right? But what you also observe is, anything that is classified as positive by this rule will also be classified as positive by this rule. Right? If you are sunny and strong, you are definitely sunny. And this may classify even weak as positive. So anything this guy classifies as positive, this guy also classifies as positive. So then what we say is, H2 is more general than H1 when this happens. So if any instance classified positive by H1 will also be classified, this is not a new bullet, classified positive by H2, H2 is more general. Or the opposite is, H1 is more specific than H2. That's my opposite. So what I will do is, I will use this kind of a relationship to make my search space smaller and smaller progressively, so that I can finally converge to the real hypothesis. So let's take another look at this, right? So these are my instances. Just some picture, doesn't mean much. And these are my hypotheses. And what I'm showing here is, the most general hypotheses are here, and the arrow shows this is more general than this. This is more general than this. If I just think of this as to be H2, this as H1 and H3, if you look at H1, what is H1? Sunny and strong. So let's say this circle here represents all instances that are sunny and strong. And X1 is sunny and strong, so this is within this hypothesis. Hypothesis H2, H3, let's say, says sunny and cool. So sunny and cool is, where did X2 go? This is sunny and cool. So this cannot be within here, right? Alright, so X2 is, sorry, sunny and light here. Sorry, this is X, I'm talking X2, not H2. X2 is sunny and light, so it cannot be within sunny and strong. This is sunny and strong, so sunny and light should be outside somewhere. That's fine. But if you look at this hypothesis H2, which says just sunny, it includes sunny and strong. So that's a pictorial way of showing what do you mean by more general than. So H2, H1 is a subset of H2 in some way. So H1 is included within H2. That's what we're going to do. So now let's come up with an algorithm to go through our search space. And the first algorithm we'll look at is find S, or find S algorithm. And this is the way it starts. So initialize our H. So the H is my what I think is the target hypothesis. I will initialize it to the most specific hypothesis. So what would possibly be the most specific hypothesis? All nulls. Right? That's the most specific. Nothing works. Never goes swimming. So if the vector of all nulls is the most specific hypothesis, I'll start with that. So I'll start with the most specific hypothesis, and now I will look at the training sequences that you have given me. In my case, we had 4 training sequences. So I will look at each training sequence and I'll see, is it a positive sequence? Am I going swimming in this one? Right? If I'm going swimming, if it's a positive, then I will look at every constraint or every attribute in H, in my most restrictive or most specific hypothesis. And I'll see, is it satisfied by this new vector X? If not, I have to include it. If it is already accepted, then no problem, go ahead. So I think it's better to visualize this, what's going on. Right? So let's see this. So I start with the most restrictive or the most specific hypothesis. That is all nulls. Right? All nulls. That's my first step of my algorithm. Initialize to the most. So this is what I'm doing. I'm starting with the most specific hypothesis, and I generalize this each time if it fails to cover an observed positive training instance. So let's see. Examples are always better. Start with all nulls. What's my first training sample? This. Sunny, warm, normal, strong, same. And the positive says it's a positive, right? And we go swimming here. Can my hypothesis accommodate this? No. Why no? Because this says I will never go swimming. All the values are null. So what does my algorithm say? For each attribute in H, if the constraint is satisfied, do nothing. Otherwise, replace AI by the more general constraint. So this is not satisfied, right? Sunny. So what should I do? I should replace this by sunny. So I replace this by sunny, I replace this by warm, I replace this by normal, and so on. So essentially, first time I see a positive sample, everything just changes to that positive sample. That's what is happening. So now what happened? If you look at your sample space, it extended all the way from all nulls. I don't know, how many do we have? 4 or 5? 1, 2, 3, 4, 5, 6. All the way to the most general one. This was my sample space, right? Everything inside was my sample space. Now what I have done, as soon as I've seen my first positive sample, I have sort of brought this boundary downwards. Right? Now this is whatever that is, sunny, warm. Can you say it? Normal? Strong? Warm? Same. Right? So now my search space has shrunk. And what I want to do is, I want to keep doing this progressively. Right? Till hopefully it converges to the real thing. Right? So the first one was simple enough. So sunny, warm, normal, strong, same, sunny, warm, stronger, whatever, right? So now what happens? One loop is done. Now now repeat the loop for the second sample that you have. This sample is also a positive sample. So what should I do? I go to my current hypothesis and see if everything is accommodated in this. This one wants to be sunny, it's sunny. Warm, it's warm. But now this wind has high here. But this says wind should be normal. So this is not accommodated in this hypothesis here. But this is a positive sample, so I want this to be accommodated. So what does it mean? Normal is not good enough. So I should generalize it. So I put a don't care condition there for the wind. So now, whether the wind is normal or high, I will go swimming. And luckily here, the rest of the three are the same in both the samples. Right? So now, I have been able to hopefully change my hypothesis space even further. Right? And then so on. Now, if you look at what find S says, it's only for positive training samples. Right? It's only for positive training samples. So it's a negative training sample, just ignore it. And essentially what that is really doing is, if you think about it, we are not really moving this part. This lower boundary is not really changing. If I had included a negative example, as we will see in the next algorithm, this would also move a bit. And then finally we have another positive thing. And in this case, sunny, warm, which is already there. This is high, but we already have a don't care, which is already included. This is strong, we already have strong here. But now we have cool and change, and this says warm and same. So these two conditions are not included in my current hypothesis. So I go from here and say don't cares. So at the end of this training, I say that this is my hypothesis that describes the data. And this will be my rule for saying whether I should go swimming or not. So now if you have a new X5, X6, X7, you will go here and test it with this thing and see if it works or not. Okay. So now let's look at some of the properties here. So the key property is, for hypothesis space which are described by conjunctions, so and conditions between the attributes, this and this and this and this, right? What it does is, it's guaranteed to output the most specific hypothesis that is consistent. We are not worried about the lower side. We are giving you the most specific. I started with the most specific one, and I tried to generalize till it accepts everything. So what I have given you at the end of this is the most specific, the most restrictive hypothesis that still satisfies my data. And that's what this is outputting. And if the final hypothesis, it will also be consistent with all the negative ones, as long as the training, there's no noise in the training examples. Right? If there is noise in the training examples, things can go wrong. And hopefully today we'll have time to get into cases when there is noise in the training examples. Why is it? Did I give you a break too early today, or what happened? Huh? Why didn't you tell me? Anyway, it's all right. When should we have had it? 10. All right, it's okay. So, what are some of the problems with this find S, right? So anytime you have an algorithm, rather than waiting for your advisor or for your reviewers to tell you what's wrong, you should think about what's wrong with it, right? Honestly, and then hopefully you're able to fix it. So one thing is, we really can't tell if it has learned the real concept. Has it converged here? I don't know. All I know is, it is giving me the most specific so far. But is it the final one? If I had more training samples, would it have changed? Maybe, maybe not. So I really don't know if I've converged or not. That's one of the things. And sometimes I want to know if I've converged or not. We want to have, we prefer a learning algorithm that can tell if it has converged to the actual real hypothesis. Or if you have not converged, then I know, what's the identity of how far am I from the real value? We don't know this. And what it picks is the maximally most specific edge. That means amongst all the hypotheses that are there, this is the most specific one. But is it really good? Why is it good? No one knows. But this is an algorithm, does something for us. So let's try to look at some other things, right? For example, I came up with one possible algorithm, one possible hypothesis which is more specific. There could be other hypotheses also which will satisfy that. So for example, it could be that the ordering of the training samples can change your hypothesis. For example, if you had seen this first, and I could come up with a toy example where if you see this first and this later, your values here will be different. So there are many of these hypotheses that are possible which will satisfy this. Which one is the right one? Which one will give us lower errors? We don't know. Right? So there might be many different specific hypotheses. We don't know. Okay? And we cannot tell when the data is in, if there is any error in the data. Maybe this was mislabeled. Maybe I actually went swimming, but there was an error. When I was recording the data, when I was typing the data, there was an error. I don't know. I cannot test, I can't figure that out. Right? And errors in the data will create problems for me. And given that you're neglecting all the negative ones, this will really create a problem for you. Right? And hopefully later on we can fix it. Right. So now let's come up with a better algorithm. Right? And in order to come up with a better algorithm, what we will do is we'll first define something called version spaces. And a version spaces, so in order to get there, it's something like this, right? So this was the most specific, this was the most general. Right now, this is my version space. So I look at, after training so much, what is my most specific, what is my most general? Anything in between is my version space. So in this case, everything is there, but as we keep learning, hopefully my version space will shrink. That's the idea. So in order to formally define that, what we say is a hypothesis edge is consistent with its set of training samples, right? If and only if h of x, whatever your hypothesis outputs, is the same as what the label is for all the data that you have for training. That's the way to interpret this. This is saying for all the data that you have for training, the output of the hypothesis is the same as the label that was given to you. And in this case, these are all consistent learners. Whatever this rule will give you, whatever this rule will give you, will satisfy all the data that is given to you, the labels of all the data. No problem. So it's a consistent thing. And the version space, which we represent as Vs of h of d, with respect to the hypothesis and the training, is then the set of all hypotheses from H that are consistent. Right? So let's look at it graphically, and that will be easier. And then let's have this algorithm, and we will see the version space and everything evolving in the algorithm itself. So this is the list and then eliminate algorithm, and hopefully this is better than our find S algorithm. And what we are doing here is, first we will start with a version space. And initially, this will be the a list containing every hypothesis in H. So when I initialize, this is my version space. A list of all the hypotheses that are there. And then what I do is, for every training example that you give me, okay, from this version space that I have, I will remove any hypothesis that doesn't match the output. So I have this is the space of all the hypotheses that I have. Now you have given me a training data. I check this. Does it match? If it satisfies my training data, I keep it. Otherwise, I take it out, throw it out. Then I go to the next one. Does it satisfy my hypothesis? Does that hypothesis satisfy my new training data? Yes, keep it. No, throw it out. And you have to go through the whole thing. But since we have this thing, more specific than. Since we have this more specific than and more restrictive than relationship, what it helps us is we don't really have to test each and every one. Once we know that something is more specific than that and it satisfies it, we can eliminate those anyway. And we'll see how that happens. So this is another way of interpreting this. So you will first list all the hypotheses in H. Then any hypothesis that you find is inconsistent with the training example, just delete it. And the new version then shrinks as more and more are observed, and it shrinks from both sides hopefully, and then ultimately you will have the desired target concept. That's the idea. Okay. Now, sometimes what happens is you want to shrink both sides so that ultimately you just have one hypothesis left. That's the real hypothesis that you want. But that will happen only if you have enough training data. If you have only one training sample, how much is this boundary going to move? Not much. Right? If you have sufficient training data, then slowly you will be eliminating, and hopefully in the end you have only one left. Right? But if you don't have, what you'll get is a range in between, maybe. Saying this is anything in this could be possible. Then you don't know exactly what it is, but you have some idea. Right? And what the advantage is, it is guaranteed to output all the hypotheses that are consistent. But you have to exhaustively enumerate all the hypotheses and then test each one. That's time consuming and not computationally very efficient. Right? So we want to do something else. So we want to have a more compact representation of the version space. I don't want to define it like this, much more simple. And the way I will do it is, I will represent it by its most general and the least general. Initially this is the only way, most general and the least general way. And then I will do this. So as an example, consider this. Let's say this is the hypothesis. And this is the hypothesis which came out of the FIND-S algorithm. And let's see what are the other hypotheses that is consistent with this particular hypothesis. And with that, I will create my version space. Okay? Now, this is sunny, warm, strong, and so on. This is the most specific one. Can I have general? For example, if you have sunny, warm, and strong, you definitely want them and you don't care about the others. So sunny and strong works. Right? Or sunny and warm works. Warm and strong works. Right? So these are intermediate hypotheses. Or these are more general than this. Right? This hypothesis is more general than this hypothesis. This hypothesis is more general than this because you don't care about this particular condition. And I could go even further. I could say just look at sunny or just look at warm. That would be the most general case. Right? I cannot have all question marks. Why? Because I definitely want sunny in there. Right? So this would be a representation of my version space. And now what we can do is, so the boundary, if you're thinking about this, this was an informal way of describing what the limits of the version space would be. If you want a more formal definition of this, what we want is the boundaries essentially. A general boundary, and I guess I have the specific boundary and the general boundary. How do I define the general and specific boundaries? And so this is the set of maximally general members. This is the set of maximally specific members. The most specific ones. This is the most general ones. And anything in between is part of your version space. So now let's come to the actual algorithm that uses these version spaces. And this algorithm is called candidate elimination algorithm. It's a bit long, but let's look at it anyway. So what we will do is, this is the initialization step. We will first initialize the boundaries, right? The maximally general and the maximally specific. Specify the boundaries. So this is initialization, and now we treat each training sample individually. So let's see what happens. And now we look at both positive and negative samples. If it is a positive sample, what do? I remove from the general any hypothesis that is incomplete. Alright, what's happened? Don't restart now. Alright, hopefully this is good enough. Yeah. So for any positive sample, so this is the specific part. Let me erase this guy. This is the specific, this is the general, right? So for any hypothesis, so now this is the positive one. If any hypothesis is in the general side that is not consistent with it, just remove it. This is general, it should include it anyway, right? So if there is anything here that is not consistent, remove it. And what do? For every hypothesis in S that is not consistent with G, so I will look at the hypothesis, set of hypotheses on the top. If you're not consistent with this, I will remove it too. And I will add all minimal generalizations. So again, like previously what we were doing, they were all nulls. I needed sunny, so I replaced null with sunny. I do the same thing. If there is something in my most specific one that is not consistent, if I want sunny here, I will replace the null by sunny. Right? I will keep doing that. And after doing that, if there is anything that is more general than another hypothesis in S, I just remove it. Okay. That's fine. And this is the same thing I do for negative. Right? I think it's much easier to look at an example and understand what we are doing rather than going line by line of the algorithm. That never works very well. So let's start this. So what does the algorithm say? Initialize to the set of maximally general and specific. So what's the most specific? All nulls, all questions. Don't cares. Fine. So now what happens? This is my first training sample. Sunny, warm, normal, strong, and so on. And this is a positive sample. This is my positive sample. So now let's go back to my thing. And we don't have to worry about this because this is not a negative example. We have a positive example. This is what I'm going to do. So first thing what I will do is, I will remove from G any hypothesis that is inconsistent with this newly observed data. So let's see. What did I observe? This is what I observed. And what was my G? This is the G. Everything is included. I want sunny, warm, whatever. Yeah. Satisfied. So this doesn't change. But now I have to go up. This is not satisfying my hypothesis. So I have to change that part. Right? And how do I change? I want that if it is sunny, warm, normal, strong, and so on, I have to enjoy. It's a positive. So instead of phi's and the nulls, I go for sunny, warm, normal, and this. I have to change it. Right? This is this part of the things that are happening. I'm replacing all the minimal generalizations that are inconsistent. So I changed it. Now comes the second training sample. This is also positive. So first I look at the most general one. That general one hadn't changed, right? This had satisfied my first condition also. This also satisfied everything on my second condition. These are all don't cares. So sunny, warm, high, strong. Oops, sorry. Sunny, warm, high, strong, everything is working. So no need to change. But I have to go up to my specific boundary now. After the first example was done, after the first training sample was done, This is my new specific boundary now. This is S1. S1 says the specific boundary after training sample 1. So now look at this and look at this. If anything is not satisfied, I have to replace it. Sunny and sunny, we are okay. Warm and warm, we are okay. High and normal, not okay. So I change it to a question mark. So I'm changing my specific boundary to something else. Okay? And then so on and so forth. The rest I think are the same. Strong, warm and same, strong, warm and same, and so on. So after 2 iterations of my algorithm, what has happened is, from all phi's and all nulls, so this was my version space in the beginning, right? All phi's and all nulls, but this wasn't there. I'm shrinking my version space, right? And what is happening is, I don't have to test each and every possible hypothesis. Why? See what has happened. There may be some hypothesis in this, right? Above this. And I didn't have to test it. Let's take a look at some more examples and that will be more obvious. Now let's look at the third training sample. The third training sample is a negative one. It's a negative sample and it says if these are there, I will go swimming. So now what happens? We work on this part of the code. If it's a negative sample, we have to go to the most specific side and remove all the specific conditions that were previously allowing this to happen. Right? Previously, anything that satisfied these question marks was classified as a positive sample. But now I have encountered a negative sample. That is not consistent with this. This is saying as long as, no matter what you give me, go swimming, right? But now this is not valid anymore because I have a negative example. I have to change this rule so that that negative example is accommodated. So that's what I'm doing here now. So now, previously this was my general boundary. Everything is okay. But now what it says is, if these conditions are there, don't go swimming. So now what should I do? For example, if it is rainy, I shouldn't go swimming, right? So I cannot have a question mark here. Question mark will include rainy. So only sunny are allowed. So only sunny. Right? Because these tell us which are being satisfied. Sunny will satisfy, rainy will not satisfy. So I have to go from here to this. Now what you will observe is, I have a number of hypotheses here. And each one of them works with this example. Right? So if I just have this rule, it will classify this as negative. Right? Because it wants sunny. You don't have sunny here. So it will classify this. Now, for example, cold is not allowed anymore. So I cannot have cold here, so I just have warm. So I say, you have to definitely have warm. Others, even if you don't care, as long as you definitely care about warm, it will fail this condition and it will not be included. And the same thing about weather conditions. Same and change. Previously, we didn't care, but now we want change. Why am I not changing the other parts and so on? Right? One thing is, they would probably violate these conditions. I don't want to change things here so that they are not included here anymore. This is the most general. Anything here should be satisfied by those guys. Right? I cannot put up a rule here which is not satisfied by those guys, because this is more general. If they are satisfying something, this guy should definitely satisfy that thing. Right? And I'm looking at the maximum. So even with one change, I can accommodate all of these things. So these are my 3 possibilities. So if I make these changes, I can move up my boundary now. And then my last sample. Where did it go? Why don't I have G4? Where is my fourth condition? Somewhere. Yeah, I guess this is my fourth condition. It's a positive thing. Right? Sunny, warm, high, strong, cool, change. And then, since it's a positive one, what I will do is, I will start at the top, and then I will look at both the bottom. So for example, come on, does anybody remember fourth one? So let me write it down before I forget. Sunny, warm, high, strong, cool, change. All right. So now let's go back here. So now if you see here, sunny, so it's a positive one, right? So I'm going to start at the top. Sunny, warm, don't care, strong, cool. We only have warm. I have to generalize that. So that becomes a question mark. And so and then we can go. So what it's doing is it's progressively, if it's a negative sample, it shrinks this side. Positive sample usually shrinks that side, and hopefully as you have more and more and more training samples, this would collapse and you have only one left. The more specific one and the general one will lie on top of each other. So now this was a general thing, very, very basic way of learning and reducing your hypothesis. One we were doing here is swimming, but you could easily imagine, for example, if you're trying to set up rules for your intrusion detection system. One case, don't allow any traffic into your thing. So these could be IP, source IP, destination IP, source port, destination port, packet length, whatever you want. One extreme case is, no packet is allowed in the network. And this is, every packet is allowed in the network. So now your question is, what IP addresses should I allow, what I shouldn't allow? So then, based on whatever training data that you have, you try to shrink it and come up with rules for your intrusion detection system or for your firewall. Alright, so now let's try to do something better. In some cases, so far what we have assumed is we had 4 training samples. Or who gave us the samples? Somebody, the teacher gave us the samples. In some cases, it may be possible to ask for new samples. Okay? Or in some cases, what you can do is you can run your own experiment and ask a teacher, please label this for me. Right? So, for example, let's say you're doing a classification of faces for male and female. You have 5 pictures, you have classified them, and so on. Now you can tell a teacher, please, you have a new picture, and you can go to your teacher and say, please label this for me. Is it a boy or a girl? Right? So sometimes you may have that choice. When you have this choice of going to the teacher and asking for one specific example, why would I want to do that? Because if my version space is quite large, I want to shrink it further. What I would like to do is, I would like to pick an example that will help me to shrink that thing. Okay? So I want to pick an example in such a way that when I go there, they will classify it, and that will reduce my version space. And this is what is called a query. Okay? So you construct one. So for example, here you have these two, right? Let's say you have trained using these 2 samples. But your boundaries are still quite far away. You want to reduce them. So what you could do is, you could say, okay, how can I reduce this? You say, okay, what if there was a training sample which was rainy, cold, normal, something, and give that to the teacher. Ask the teacher to classify that. Then hopefully you can shrink it. And that's where the where your smartness comes in. You want to ask the right question. I could create any possible training sample and say, please classify this for me. But if this is an expensive process, right? If it's a medical image, you want to know if there's a tumor in that thing or not. You have to go and ask a doctor. And if the doctor is not your family or friend, they may ask you for money. Right? So you only want to give a picture which will help you the most in order to learn. You don't want to give some random picture and say, please classify. So that's important later on. If I have the chance to ask a specific question to the teacher, that will help me reduce my boundaries. What should be the question like? Right? Which will help me the most. And that's where we are coming here. So, what should be the best training example to ask here? Okay? And the answer really is, what you want to do is, you want to ask a question such that half of them will satisfy this, half of them will not satisfy this. It's sort of equivalent to doing a binary search. Right? You have a whole range of things, right? So what do you do in binary search? So let's say you have a number, something between 0 and 1000. Right? This is your range. You pick a number and you ask, is it on the top half or in the bottom half? Right? And the teacher will come and say it's in the bottom half. Then your search space is reduced by half here. Then you make this as half and ask a new sample in this range, and then you say, is it here or here? And the teacher says it's here. So progressively you become smaller and smaller, and you need log to the base 2 of n or something like that to converge. The same thing happens here also. You have to look at your examples, and I have a problem in the end where I'll show you how to do this. What you want to do is, you look at this boundary and this boundary, and you say, what can I ask so that either this will move here or this will move down here. Then you will ask a question crafting based on this. In many cases, for example, you would give a different one. Instead of strong, you give a weak noun. Right? Or rather, this is a question mark, you are allowing anything. Right? You are allowing anything here. Give a specific value here. In the general case. In the general case, the boundary says, I don't care about the value of the prediction here. Give a more specific case and see if it changes or not. Okay? That's what we're trying to do.
Is training on the true data set will be better or the false will be better?
Yeah, so in this case what we have is we have a set of training data. I have trained it. That has given me some range. I want to reduce that possibility. So you have a choice. You ask me a question.
It is false. If I have more instances true, then I can go for the false.
You could go for a false. So you have to craft, it depends on, that's correct. So you have to see what question will reduce it, hopefully by half. You want to reduce the uncertainty by half every step you go. Yeah.
So in that case, which sample will be the better one?
What I'll show you is, usually what happens is, you want to go one attribute at a time. Right? Especially if your attributes are binary. You ask one attribute, which is right now ambiguous. You ask it to classify that attribute. When it's classified, now you know whether it's positive or negative. So it has shrunk by half. That's the way. Okay. Another thing is, how do we use partially learned concepts? So for example, in my case, in the example that we did, we had only four training samples, right? So we haven't really converged to the real concept. We have a range of concepts. So I haven't learned it exactly. So it's a partially learned thing. But can I still use it to classify things? Can I use it to really test things on? The answer is yes and no. Sometimes you will be able to, and sometimes you may not be able to. Right? Sometimes it's possible to do with a certain degree of confidence. Right? Just as an example, let's say I have learned this far. This is my specific boundary, this is my general boundary. Right? I don't have a single one. Anything in this will probably work. Now let's say I get a new query saying sunny, warm, normal, strong, cool, change. Classify it. Is it a positive or a negative? So then what I can do is I can go and say, of course this will be classified here. Right? This is sunny and warm, both are satisfied, so we go up. What about here? Sunny, warm, strong. Sunny, warm, strong. So it's satisfied by this boundary and this boundary. So I know that it lies somewhere here. So both my specific ones say yes, both my general ones are saying yes. So I classify this as positive. So I'm fairly confident that this is a positive one. Raining, cool, normal, light, and so on. It will be rejected here, it will be rejected here too. Both want sunny to be there. So I'm going to classify this as a negative sample. With reasonably good confidence, I will say that this is negative. The last one, sunny, warm, normal, and so on. So sunny, all right, warm, all right. So this will say it's positive. And let's look at this side. It says sunny, warm, normal, sunny, warm, whatever. But this is light. Am I doing it right? Yeah, this is strong. So this is not satisfied. So now I'm somewhere here in the middle. I'm definitely not in the entire version space. So I know that this is not convinced, I'm not sure. So let's try these guys also. Sunny and strong, not satisfied. Sunny and warm, satisfied. Warm and strong, not satisfied. So I don't know what to do. So in many cases, what we will do is we can sometimes take a majority vote. I look at how many rules that I have, how many hypotheses that I have there, and if the majority are saying it's positive, I say it's positive. If the majority are saying it's negative, I say it's negative.
So more learning kind of models are required for.
So here what you really need is more training samples. You haven't trained your model enough to really classify everything. So there is an ambiguity here and you don't know. So the best you can do is give some kind of confidence. 50% chance that this is positive or 70% chance is positive, 30% negative. Based on how many are classifying it as positive, how many are classifying it as negative. And the other thing that we have is, I was talking about this a little bit, and this is fairly important for you to understand, is that there is a bias in the hypothesis here, hypothesis space. I'm saying this is my entire hypothesis space. But this is the entire hypothesis space of conjunctive hypothesis, where you have AND conditions. You believe that your final hypothesis is a conjunction. Who is to say it's a conjunction? You assume that it's a conjunction, right? So you're limiting or restricting your search space. So in this case, your thing will work only if this is in the search space. If it is not, what do you have to do? You have to enlarge your hypothesis space. You have to search for bigger spaces and so on. And that's the only thing. And just as an example, we have this. Let's say these are my training samples now. Right? We have 3 examples. And what we want to do is we want to choose a hypothesis that expresses everything here. So if I take this and I go back to my original classification that we came up with the tree, you will see that it satisfies some of them and it doesn't satisfy some of them. Right? So now, if you want an unbiased learner, what should I do? I should include all possible hypothesis space. And how does that work? essentially you have to include the power set of x. Right? X is the set of instances. You have to include all possible subsets of x. Right? You have to worry about this power set. And then, so essentially you have to consider a hypothesis space which includes disjunctions, conjunctions, negations, and everything else. So now your hypothesis space may look something like this. You want it to be sunny, warm, and normal. I don't care. Or, I don't care, there's a change, there should not be a change. Right? I don't care what the weather is like, what the rest of the parameters are, but the weather should not change. As long as the weather is going to be constant, I can go swimming, or as long as these three are there, I can go swimming. So this is a much more general hypothesis space. And you know, if you go back to your trees and so on, and you try out these three test conditions, they will not be satisfied. But hopefully, if you're not generalized to something like this, you can come up with a set of rules where it works. And another way, so we were talking about biasing, right? So we said the bias really was that I restricted my search space or hypothesis space to only conjunctions. How do I formally characterize this bias? Right? In most scientific things, if you say that there is a bias, then you should be able to characterize the bias. What is the way to characterize the bias? What is the formal definition of bias in this case? So again, let's see what we have. We have an algorithm L, maybe find S or candidate eliminate, whatever you have. You have some algorithm L. And then you have your training samples and the target concept. These are the instances and the target. And what you have is, these are the training samples where you have the X and the output of X. Fine. And this is the classification that you assign to a particular input sample. Now, what is the bias? Right? What is the bias? So what was the problem previously? The problem was you have restricted your hypothesis space to only look at conjunctions. And the real life system is not conjunctions. Maybe it's conjunctions and disjunctions and disjunctions and knots or something. Right? The real concept is more complicated. That's what we're assuming. I'm only searching for conjunctions, but the real stuff is more than just conjunctions. So what bias says is, what extra set of assumptions or assertions do I need so that I will be able to figure everything out? I will really get the actual rule or concept. So to my current set of rules or current set of assumptions, what extra thing do I need to add, this B? For example, here, the extra thing that I had to add was disjunctions and negations. Okay? So what extra thing that I have to have, so that for all my instances, I will be doing the correct classification. That's the bias. This is just a mathematical way of saying that, you know, what extra thing you need to add to your current set of assumptions so that you figure out the right hypothesis. Let's look at three examples of learning tools, very simple ones, and see what their bias might be. One simple one, a very simple algorithm might be a rote learner. It just memorizes things, it doesn't do anything else. So every time it gets a sample, training sample, it records it. That's its learning rule. You give me a training data, I will record it. I have learned it. How will I classify test data? You give me test data, I will look through my list. Have I seen the exact same data before? If yes, then I know what the answer is. If I haven't seen the test data before, I can't classify. So you can imagine that most of the time this will not work in practice. Right? This only works if you have seen this thing before. It doesn't work on new things. But it has no inductive bias. It doesn't assume anything. It has not made any kind of assumption on any hypothesis space. It hasn't said that the, whatever attributes I've seen, they should have been an and or an or whatever. It just says if it is there, if I've seen it, I know it's part of the thing, so I will classify it. And then the candidate elimination algorithm, we have been talking about this. Here the assumption was the target concept can be represented in its hypothesis. So I started with the assumption of conjunctions. So as long as the real concept is a conjunction, I will find it. That was the assumption. And the find S thing. In the find S, remember what happened? I was only looking at the positive samples. I wasn't looking at the negative samples at all. Right? So in this case, it's a little bit more. First thing is, we are making the same assumption as candidate elimination, that whatever space I'm searching, the real thing is definitely in there, so it's conjunctions. I have made that assumption, just like here. But I have also made this thing about negative instances. I'm not dealing with them. What I'm saying is, all instances are negative instances unless I know. I only worry about the positive, and if I have not seen it, it's a negative instance. Right? That's a bigger bias.
Rote learner and find that they are almost same.
It's not almost the same because here you are generalizing. You are putting in question marks. Right? So you're right. It's in some specific examples they may turn out to be the same, right? But not always, not necessarily. Right? So in the example we are doing in class, maybe I have to work through it. In simple cases, it may turn out to be the same, but no, this is in general. This is more specific, and this is more general. Okay. So now what we'll do is we'll move on to the next one, which is called decision tree learning. And now, so far in the discussion, we have no noise. We assume all the training data is correctly labeled. Right? But now we'll generalize it a little bit and see how we can handle noise also. So we'll go to decision tree. So this is one of the more popular inference algorithms where we try to classify things. And what is this is a method for approximating discrete value target functions. So not continuous. So your target is discrete value. It's essentially we're doing classification. We are not doing regression here. We are doing classification. And the learned function. Last time, what was our learned function previously? It was a set of conjunctions. Now, instead of putting it as a conjunction, I will draw it as a tree. Right? It will be represented as a tree. And that's usually much more easier for humans to see and learn and visualize. All right, I don't have it. So, what is the representation here? What am I doing? Previously, I was testing the attributes, right? I was saying it is sunny or rainy. So what will happen here is, at every step of my tree, so a tree is like this, right? Let's say these are my attributes. So what was it? Sky. Anybody remembers? Let's make it up, right? Sky, temperature, humidity, wind, forecast, right? And maybe something else, it doesn't matter what. Water temperature, right? Something. Anyway, I don't have space, so that's fine. So these are my attributes. So what I'll do in the graphical model is, I will start by testing one of these attributes. Which one should I test first? We'll spend quite a bit of time on that. Right? But I will test one of those first. Let's say temperature. I will test the temperature attribute. Temperature was high or low or something like that, right? So I will see. Are you high or are you low? If you are high, then I'll test something else. Maybe in this case, I will test wind. And if it is low, maybe I'll test the forecast. And if the wind is strong or weak. And maybe if the temperature is high, wind is strong, I should say strong and weak here, maybe I will say this is a positive sample. Go play tennis or whatever it is, go swimming. If it is this, no. And similarly for forecast. Maybe for forecast, I now have to look at the sky. Right? The depth of my tree doesn't have to be the same in all the branches. But this is the idea. At different nodes, I will test different conditions, and based on the path you follow, at the end of each path will be a classification. So you start with your testing with different attributes and follow a path, and when you reach the end of the path, you will know what to do. And the main thing here really is, which one should I test first? Is temperature more important or humidity more important? And we'll try to classify that. Anyway. So this is one way of looking at it. So I can first look at the outlook. And outlook has three possible answers. And it says if it's overcast, go play tennis. And if it is sunny, then I look at the humidity. If the humidity is high, then I don't play tennis. If the humidity is normal, then I play tennis. If it is raining and it's windy, then I don't play. But somehow, even if it is raining, I still play tennis. I wouldn't do that, but anyway, that's fine. So when should we use decision trees as compared to other machine learning things? Right? When should I be using this? In general, when your instances are described by attribute value pairs, like here, temperature, this is my attribute, and I have values high, low. When you have things like this, let's say you're trying to find the medical condition or whether a patient has a certain disease or not. So you can check temperature, high, low, or medium, something like that, right? Blood pressure, this. This test result, positive or negative. And then you can hopefully classify whether the person has whatever, dengue or not. So that's it. And the target function should also be discrete valued at the end. If it is continuous value, it doesn't work so well. It doesn't work actually, does it? And in this case, disjunctive hypothesis is okay. Right? So for example, this is high temperature, strong wind. And we can also put OR conditions here. Okay? So you also go, let's say, here. So this or this will give you a positive answer. We could do disjunctive things also. And sometimes, even when training data has some missing attribute values, you can still live with it. Not a problem. And we'll see how we handle that in the end, if we have time. No problem. And some of the examples, for example, when you're doing equipment diagnosis, is your equipment faulty or not faulty? You can check that using these decision trees. So you check a number of sensor values to classify whether this is okay or not okay. Right? Or medical diagnosis that I was just talking about. Credit risk analysis. So I don't know how it happens here, but in many places, let's say I want to go and buy a house. I don't have the money, so I have to go and ask for a loan from the bank. Somebody in the bank will be sitting there and making a decision. Should I give this guy a loan? Is he going to repay back the loan, or is he at risk? If he thinks that I'm risky, then I wouldn't get the loan, right? So what would they look at? They would look at my past history. They may look at my current bank balance. They may look at whether I have a job or not. So they have a decision tree. Does he have a job? Does the job pay more than this? Does he have a collateral or whatever, right? And then you'll finally decide, should we give loan to this person or not to that person? So let's start with the basic algorithm for decision trees. Right? This is the fundamental decision tree algorithm. So what we have to do is, so this is the main loop. We have some initialization and other things, we will worry about that. So initialization says pick a root. We have to pick a root node. How? How we pick a root node is the same as the next node, so we don't worry about it. But let's look at the main loop. Right? What you have to do is, what you want to pick. So let's say I'm here, forecast. I can choose between sky and humidity and whatever, right? Which one should I pick? It says you have to pick the best decision attribute. Whether it should be sky or temperature or not temperature, I mean humidity or whatever, pick the best. So far I have not said how to pick the best, we'll come to that. But idea is somehow you will pick the best one. And there's a way to pick the best. So you will pick the best decision attribute. And what you will do is, you will assign A as the decision attribute for that node. So here, for example, I had, at the root, I had a choice of sky, temperature, humidity, whatever, N, this is humidity, wind and forecast. Which one? Pick the best. Some way of, will define best. And once I have picked the best one, the best is temperature. So I have picked temperature here. And that's what it is saying. Pick the best as the decision attribute. So temperature is the decision attribute for this particular node. And here, for example, forecast is the best decision attribute and so on. And for each value of A, we create new descendant nodes. So temperature, what are the values? High and low. Right? So I have descendants here, 2 descendant nodes. Fine, so that's rule number 3. And then we'll sort the training examples to the leaf nodes. So what does that mean? So when I was here, in our previous example, right, what did we have? We had 3 positive examples, 1 negative example, right? When we were doing that swimming thing, we had 3 positive, we had four training data. We had 3 positive and 1 negative. Right? So what this line is saying, line number 4, now you have split high and low. Some of the positive samples will come here, some of the positive samples will go here. Some of the negative samples will come here, some of the negative samples will go here. How many of the positive samples came here? Maybe 1, and maybe none of the negative samples came here when you break it down. But here, the remaining must be here, right? So this is the 2 positive, 1 negative. That must come here. So this was all your training samples. But when you split, you see which ones had high temperature, which ones had low temperature. And based on that, you split. Okay? So that's what you're doing here. And then you check, there's a stopping condition. If you see that all your samples have been perfectly classified, you stop, you have your tree. Right? If not, you find the same thing for these nodes. In the best case, maybe just by looking at the temperature, you can classify everything. Maybe the temperature decides, and other things don't matter. In that case, you could probably, if it's high temperature, you go swimming. If it's low temperature, you don't have to go swimming. So for example, if this was, all the positives came here, and all the negatives went there, you probably don't have to do anything. You have classified everything, or something like that. You get the idea. All right. Questions so far? Okay,
So,
Yeah.
So anything related to branching factor? Because the tree that you show on the slide was having 3 nodes in the first, and here you have drawn only 2.
Oh, yeah. So it depends on how many values are there. So if your attribute A has 5 values, you'll have 5 branches. Is that what you're trying to ask?
Yes, sir.
Yeah. So I just assume temperature is 2 values, high and low. If there was a medium, then you'd have a third branch. The number of branches depends on how many values your attribute has. If it is binary value, 2 trees, 2 branches. If it is ternary, then you'll have 3 branches and so on.
So next you will take entropy calculation.
That's right.
Yes.
That's right. Yeah. Okay? So now the question is, how do I pick this best guy? Or the best node, girl, whatever, right? How do I first pick the best attribute? And this is just as an example. Let's say I have 2 attributes, A1 and A2 to test. Here I had 5 attributes. Yeah?
So actually I want to know, there is a difference between these rules and those hypotheses, which is initially we have studies about those hypotheses and these rules.
So ultimately, this will be one hypothesis. This will be an hypothesis. Or you can think of the whole tree as a hypothesis, actually.
So even we have, here we have limited hypothesis, and that place there are so many hypotheses are there, because there's large space for hypothesis.
That's right. And in this case also, you are not really restricting your hypothesis. What you are saying is, if this is there, and this is there, and this, or this, and this, and this. So in some sense, this is actually more general than my conjunctive hypothesis cases.
So that means if it's a complete binary tree, it will generate the entire...
It will generate all possible combinations, right? All the possible. If your data is so crazy that everything is different, then you will just keep branching, and so on. So here what is there is, I'm not implicitly assuming anything. I'm just trying to look at, so for example, the rote learner thing. It just looked at it, and if it has seen it, then it classifies it. Did it assume anything about the hypothesis? Not really. So in some sense, it included all possible hypotheses. Here also, I'm also not saying that it should be just ands. It could be ors. So this is actually more general. I've not assumed any bias on this so far. All right. So now let's consider here I had 4 different attributes. Now let's say I have just 2 attributes here, A1 and A2. Right, so then what happens? This is all my training samples here. So 29 plus 35 is how much? 64, right? So I have 64 training samples in this case. I have 64 training samples, and in those 64, 29 were positive, 35 were negative. And if I test using attribute 1, let's say attribute 1 can be either true or false, of the true ones, 21 are positive, 5 are negative. And of the false ones, 8 are positive, 30 are negative. And if you look at the other attribute, overall nothing is different, right? The samples are still 64 and 29 are positive, 35. But here, the true ones are 18 positive, 33 negative, and 11 and 2. So now your question is, at the root, should I be testing for A1 or for A2? Okay. And the answer to that comes from the field of entropy. And it says this. Let's say P positive is the proportion of positive examples in S. So in this case, P positive would be 29 over 64. And that's the proportion of positive samples. And P negative would be 35 over 64. So that's the proportion or fraction of negative samples. Now what entropy does is, so entropy measures different, depending upon which area you're from, if it will mean something else to you. In some sense, entropy measures, this is coming from an electrical engineering background. By the way, electrical, when I say electrical, it means electronics, right? So coming from an electrical engineering background, to us, entropy means information, right? How much information is there in the thing. If you're a thermodynamics person, it means how much disturbance or how much the molecules are moving and so on. Right? Another way of saying is how much impurity is there. If everything is the same, then there is no, everybody is the same. No impurity, nothing, entropy would be zero. That's the idea. If there's more variation in the thing, entropy would be higher. I say.
So how that formula is derived?
So the way this formula has been derived is we think of this as coming from information theory, right? So what this P1 is, or P positive and P negative is, it's the fraction of positive and negative samples, right? So what this says is this log to the base 2 thing, right? Log to the base 2 P2. It comes from coding theory. It says that, okay, let's say you're going to send messages. I don't want these guys. Let's say you want to send messages, right? And you have messages like this. A, B, C, D. These are the 4 messages that you can ever send. Right? All your information is just 4 things. A, B, or... So you're sending a message to me, it can either be A, or B, or C, or D. And let's say I want to send it as binary. So then you say, how many bits do I need for this? You can say this I can represent by 0, 0. This is 0, 1, 1, 0, 1, 1. So what this says is, I need 2 bits to represent the messages. Right? That's what it says, 2 bits per message. But then, if I'm an information theory person, I say, okay, is this really the best? Can I do it with smaller? Can I still send you these 4 messages? But on an average, I will spend less number of bits. If I do this there's no averaging thing. Always 2, right? So then as an information theorist, what I think is, okay, are all of these messages equally likely? Do we send A 25% of the time? Do I send B 25% of the time? Do I send C 25% of the time? If it is like that, then you have no way, you have to do this. But let's say you send this 50% of the time, something like that. 50% of the time you only send A's. And let's say something, which I can calculate, or which is easier, right? 30% of the time I send B. Or let's make it more, it's fine, right? And maybe this is 10% of the time, or 9% of the time. Does it add up to 100? No? Last one is 11, right? So let's make it 19, let's say, something like this. So what it is that most of the time, or if I don't like this, so let's make this even a more extreme case, 80%, let's say 10%, and then this is there, right? 9 and 1. So 80% of the time I'm sending an A. So instead of coding, this is my coding. A is 0, 0, B is 0, 1, this is this and this. Instead what I could do is, I could just represent this by a 0. I could represent this by a 1, maybe. Right? This by a 1, 0. And maybe this by a 1, 1. Or rather, actually, this is not a right way of doing the code, maybe. Something like this, maybe. This is not a valid, but I'm just trying to give you the idea. This may not be a valid code. You can probably complain to me later that is not a real code. But the idea is this. For the most common one, I use only 1 bit. And for the most rare ones, I use more bits. But on an average, what would happen? You multiply 80 with 1 and this with this. So your average will be less than 2. Okay? That's what this is saying. So what information theory, what Claude Shannon says is, the best you can do, so this is something I wrote up at random, which is probably wrong, right? But the best code that you can come up with will need log to the base 2 number of bits. And how do you find the average? Probability with the number of bits, right? So how do I find expectation? X times P of X, right? And then I sum it up. That's what that thing really is, right? Log to the base 2 P2 is sort of X, and P of X is P of the error. Okay, that's where it's coming from.
So that's why we are putting a negative sign.
Yeah, the log of, this is, probability is less than 1, so that's going to be a negative number. So, that's what it is. Alright, so yeah, okay, I thought I missed the first negative, but I haven't, so that's good. Yeah. So this is a measure of the entropy. Right? This is a measure of how much variation or other things are there in my data and so on. So what I will do is essentially the expected number of bits to encode this. And this is what you're asking because the optimal code length assigns log to the base 2 p bits to code messages which occur with probability p. That's fine. And this is what your entropy would look like if you just have positive and negative. So if any of the probabilities is 0, that means if p positive is 0, that means p negative should be 1. If all the samples are negative. If all the samples are negative, there is no uncertainty here anymore. Your job is easy. There's nothing to tell. Everything is negative. So entropy comes out to be 0. What's the biggest uncertainty you can have? 50-50. Could be positive, could be negative. I don't know. In that case, your entropy reaches a maximum. And even if you think it's 80-20, it will be something lower. And that's the idea here. More uncertain your thing is, higher the entropy and so on. Fine. So what we want to do is, I want to pick an attribute that will reduce the entropy the most. What I want really, I want to classify, right? Ideally I should be able to say this is positive, this is negative. I don't want any uncertainty in there. So I want to reduce the entropy as much as possible. That's what I want. If everything is properly and exactly labeled, there's no uncertainty. So what I want to do is, I want to pick the attribute which will reduce my entropy the most. And the way we calculate this, we calculate something called the gain. So what I'm doing is, if you look here, what was the initial entropy I started off with? That's here, entropy of S. This is the initial entropy I started with. If I go this way, what will be the new entropy here? If I go this way, what will be the new entropy here? Then I sum them up. That's what is happening here. For each value of A, I'm summing this up. This is true, this is false. These are the two values of A. Right? So for each value of A, I'm going to sum up this entropy and this entropy. But then you also have to weight it. By what? How many samples are actually going this way? That's this part. Of the total number of samples, which is 64, how many samples are on the true side? This is the fraction of samples coming here. Like how I've related it. Right? These guys. 21 plus 5 is 26. So SB here will be 26 and this is 64. And for this guy, it will be 38 over 64. So this is the entropy I started with. And when I go here, these will be the two entropies. I weigh them by the number of samples here and the number of samples here. That's what I'm doing. And I take the difference. So that's the reduction in the entropy. So what I will do is, I will say, okay, if I use A1, what is the gain? What is the reduction in the entropy? Then I look at A2. I see what's the gain, what's the reduction in the entropy. Whichever is more, that's my test, that's my best attribute. Okay? So I have this, I did these last night, so calculating these entropies is a hassle. So anyway, so I have written them down, so we won't waste much time doing that. Let's look at it. So let's look at that. So what do we have? A1, and this is true, this is false, and this is A2, this is true, this is false. Right? And for both of these, we have how much? 29 and 35. Negative samples. So what is my entropy in the sample itself? It's an E of S, right? So it's 29 over 64, negative, log to the base 2. I'm not going to write the 2, you know it's a 2. 29 over 64 minus 35, 64, LOG, okay, LOG, not NGO. 35 over 64. You figure it out, and there you go. 993. And you see that the entropy is quite high, and you can see that it's not 50-50, it's not 32-32, but it's close enough. And so the entropy is high enough. And now what I will do is, I will see, okay, if I go here, then I get 21 positive, and 5 negative, and 8 positive, and 30 negative. And I have 18 positive, 33 negative, and 11 positive, and 2 negative. So now let's just do one in the interest of time. Oh crap, we have just 10 minutes. Anyway, we'll do it anyway. So what is the gain of A1? Right? This is entropy of S itself, which is somewhere 0.993, right? This is entropy of S minus that thing. And we have two cases, this and this. What is SV here? How many samples are coming? 21 plus 5. 26, right? Over 64. Right? And then the entropy. What is the entropy? 21 over 21 plus 5 is 26. Log 21 over 26 minus 5 over 26 log 5 over 26 minus this side of things 38 64 and 8 over 30 no 8 over 38 log 8 over 38 minus 30 over 38 log 30 over 38. Right? And if you crunch out the numbers, this will come out to be 0.268. And similarly, you can do gain of A2. And this will come out to be 0.124. So this is higher. So I'm going to select attribute A1 as my root node. The root, I'm going to select A1. Okay? And we could go up with our training example like this. Right? This test something which says I have a set of 14 samples. Right? I have a set of 14 training samples, and in each case I have 4 attributes: outlook, temperature, humidity, and wind. And here I have, for outlook, I have three values: sunny, overcast, and rain. Here I have hot, mild, and cool. Again 3. High, normal, high and normal, I guess, and then so on, right? And then I have a label for each one of them. So then we can actually characterize a tree for this case, and let's see that. At the very top, what should be my root? I have to test all of these 4. Here I tested 2 attributes. I have to test all 4. So if you look at the sample here, I have 14 samples. If you count through this, there are 9 yeses, I hope, and 5 no's. Right? There are 9 yeses and 5 no's. So in the sample itself, what I have is this: 9 and 5. And I can calculate the sample entropy. 9 over 14 log 9 over 14, 5 over 14 log 5 over 14. Comes out to be 0.94. Now what I need to do is I need to test each of the 4. Humidity, wind, and the other 2. Now if you look at humidity, if you look at high, when the humidity is high, these 4, we have 2 no's and 2 yeses. Humidity is high, we have another no. Humidity is high, another yes. So I think 3 so far. Humidity is high, 1 no. So 3 and 4. That's what it says, 3 and 4. When the humidity is high, I have 3 positives and 4 negatives. And when the humidity is normal, 1 positive, 1 negative, 2 positives, 3 positives, 4 positives, 5 positives, 6 positives. 6 positives, 1 negative. Right? That's the way to interpret the data. And you can do it for wind, and you can do it for whatever, right? Humidity and so on. And then you can calculate what is the gain if you do this. Just like we have done here. Right? And similarly for outlook and temperature. I just drew 2 of these, but you would have 1 for outlook, 1 for temperature. And now you have 4 gains: 0.15, 0.24, this and this. It's obvious that outlook has the biggest gain. So what I'll do is, my root would be outlook. And if root is outlook, I have 3 possibilities as values. So I have 3 branches here. And if I go on the sunny branch, these are the samples of the 14 that I had initially. These are the ones that satisfy the sunny outlook. These are the ones that satisfy the overcast outlook. And these are the ones that satisfy the rain outlook. So now the question is, what should I be testing here? Life is easy here if you look at overcast. When it's overcast, it's always positive. So I'm done. The decision is yes. So I don't need to grow this tree, this branch any further. I'm done. I need to think, what should I test here and what should I test here? But here again, outlook is done. So I have humidity, temperature, and wind which are left. Right? So I'll be repeating that. So I have to do, for example, at this point, I have to consider humidity, temperature, and wind. Again, I have to calculate the gain. Small difference. Initially, my sample entropy here was 9 and 5, right? But now when I calculate the sample entropy, it will be with this. My sample entropy now is 2 and 3. Calculate the entropy with here. So when I calculate the gain here, this is the gain when I consider the sample to be only sunny cases. And this is the attribute. Okay? So what is happening here is, if you calculate the entropy of this, 2 and 3, 2 out of 5, 3 out of 5, it should be 0.97. Right? That's the entropy of this guy. And if you look at what happens when you're looking at humidity here, I guess 3 would be positive, and 2 would be negative or something like that. Right? And in this case, let's look at this, D1, D2, D8, D9, and 11. What's happening at those? And I want to look at humidity. Let me write it down, or one of you has to remember. 1, 2, 8, 9, 11. Right? And I'm going to look at the humidity aspect. 1 and 2, humidity is high. No. Right? 8 and 9, humidity is high, answer is no. 11, doesn't care. Right? So what it says is, whenever the humidity is high in this subset of samples, answer is always no. Right? So if I were to draw that thing here, so I'm coming on the sunny branch, right? And now let's say I'm checking humidity. That's it. Humidity, right? High and low. Or normal, right? Normal. When the humidity is high in these samples, the answer is always no. And when the thing is normal, the answer is always yes. Right? So you don't have two different things here. It's all positives, whatever positive, and 0 negative. And here you have 0 positive, whatever negative. 3 negatives, I guess, right? And 2 positives. What is the entropy here? You would get a form of 0 log 0. Right? Well, and I should have it defined somewhere, what I mean by 0 log 0. Or I don't have it. It's 0. Okay, that's how we define it. So that's why if you keep going, the entropies are all zeros here. So it will be 0 log 0 and 1 log 1. Right? 0 over 3, log 0 over 3. So that's 0 log 0. And 3 over 3, logs 3 over 3. 1 log 1. This is 0. So that's why these are coming out to be 0. But anyway, the idea is now you have figured out the gain of all the 3. And which one is the best? This guy is the best. Why? Because it's classifying exactly, there's no ambiguity here anymore. If you use humidity as the discriminator now, you can exactly classify without any problems. And that's why the gain is so high. That's the way to interpret this thing. Right? So in the next one then, you would, this would be a humidity box. Okay? All right, it's your lunchtime. I'm very sorry. So I was hoping to cover more and hopefully do an example or two in the end, but we'll pick up tomorrow. That's fine. Okay? Any questions so far?
What is it that coding part, variable name Huffman coding can be used there?
Yes, you could do that if that's the optimal code. By the way, if you want to play with this decision tree thing today, right? So what you could do is, but these are all MATLAB based. I'll do this problem tomorrow. That's fine. So if you want to, so the algorithm that we just did, right here, it's called ID3. If you go to this website, you will get the whole code and you can play with it. It's in MATLAB though, so if you don't have MATLAB, then you're in trouble. But there are many other languages which would define this. Okay. So yeah. By the way, this guy is Tom Mitchell, and he has one of the most popular books on machine learning. Many of the things I'm teaching you here is from Tom Mitchell's books. Right? So initially they had a Lisp. Somehow this is shutting down, but that's okay. Initially he had the code in Lisp, but I guess nobody uses Lisp anymore. So he has moved it to MATLAB. So if you want to play with this and see what are the impacts of different things, there is code here. All right, then I'll see you tomorrow.
Everyone please submit the registration forms. today is the last day for submission of registration forms. किसने नहीं किया ना फॉर्म को अंदर और से निकाल पाएंगे
So, if I ask you to put a number between 0 and 7, there are 7 possibilities, right? You need 3 coming from now. So here that's what you're saying. No, yes, question mark, or high, medium, low. Still a lot, right? Sorry? Information gain, I don't think so. It came out to be negative. Because what Bayesian statistics, yes, you can do it. If you knew the priors, like, if you know the probability that Indian average these many are cloudy days, but you need that. Here you don't need that. It depends on what kind of data you have.
बाहर
I will do it right now.
कुछ है क्या चिपकाने
चंद्रभूषण कुमार
No, you won't be able to find it. But I'll do this after I've uploaded. I'll send an email to Hari.
गुरुचरण सिंह
I would wait for that. Because I've been told no. Somebody. So one of the things no, it's sparse learning. So like I was saying that you have a matrix, most of them are zero. You have many sensors. So even when most of the inputs are zero, I will still want to figure something out.
तो फिर लैपटॉप में दिखा हाँ